Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying functions lecture 8. In this lecture we'll be talking about properties of odd even functions, inverse functions, functional equations and PNC based problems. Okay.
Now let us try to understand one property of a function that says any function fx can be represented as a sum of odd and even function. So before explaining this property, I'll take few examples. Let's say we have fx plus f of minus x. Let's say this function is called gx. And if I try to write g of minus x, then I'll get f of minus x plus f of x, which is nothing but gx. So basically, this is an even function. G of x equals to g of minus x. This is an even function. Now let's take one more example. Let's say hx equals to f of x minus f of minus x. Now if I write h of minus x, we'll get f of minus x minus f of x. That is nothing but minus times fx minus f of minus x. This is minus hx, right? So we can see that difference one is an odd function. Now if I try to add hx plus gx, what will I get? I'll get 2fx. And if I write fx equals to hx plus gx by 2, then we get to understand the property of function fx. We get the same thing, right? Any function can be represented as a sum of odd and even function. So basically, if I want to write a function in terms of as a sum of odd and even function, what I'll have to do, I'll have to write in terms of this manner. So let's remove this and let's take one example. So let's take one example of fx equals to e raised power x. So basically f of minus x equals to e raised power minus x. Now if I try to write fx in terms of both these, so both of these, what I'll do, I'll write fx equals to e raised power x plus e raised power minus x divided by 2 plus e raised power x minus e raised power minus x divided by 2. So these are two functions, right? And we got to see that this one is an even function and this one is an odd function. So basically we wrote e raised power x as this one, summation of even and odd functions. So this is our property. Now let us look at one illustration. We have been given fx equals to ln x plus 1 plus x square. So this is the whole under root. Now the first step is to write f of minus x, right? ln minus x plus 1 plus x square. This stays the same because it's x square. So whenever I see something of this sort, a plus root b or a minus root b, then I tend to think about rationalization. So I'll do the same over here. So we have x plus under root 1 plus x square. And what I'll try to do, I'll try to rationalize it. So I'll do minus x plus 1 plus x square divided by minus x plus 1 plus x square. Now if I multiply both of these, what I'll get, minus x square plus 1 plus x square divided by minus x plus under root 1 plus x square. So this gets cancelled. So what is this? So basically this is 1 by this. So this comes out to be 1 upon minus x plus under root 1 plus x square. So this is same as this, right? Now what we got, f of minus x equals to ln. I can write this as this raised to power minus 1, right? X plus 1 plus x square, this raised to power minus 1. Now we know the property of log that if we have something in power, it can get carried over here. So this is minus 1 into ln of x plus 1 plus x square. Now this is nothing but minus fx. So we got this as an odd function. So I'll try to summarize this once again because it got a little messy over here. So what I did, I did f of minus x over here and we got minus x plus root of 1 plus x square. Now whenever I see something of this sort, a plus root b format, I try to rationalize it. So I rationalize it. Then what I got to know that this entire thing is nothing but 1 divided by this one. So basically I can write this as this raised to power minus 1. Minus 1 got carried over here because of the log property, and that is how f of minus x equals to minus fx. Now let's talk about inverse of a function. So our hypothesis is inverse of a function exists only when the function is bijective. Now let's try to prove it. So basically we are saying that if a function is 1 1 and on 2, only then we can say that inverse of a function is going to exist. So let's take again example. So this is our set A, this is our set B, this is our set. Yeah. Now let's say this is the inverse function. So we are defining from B to A. We talked about inverse relations in our previous lecture, right? So we just change the direction of arrow. Now let's discuss the case of many one function. Why many one function cannot be invertible? So let's say all these elements are being mapped. So A is being mapped to 1, B is being mapped to 1, and C is being mapped to 2. So we have no mapping for 3. Now let's try to invert it. For inverting it, we just have to inverse the arrows, right? So now this is happening, right? Now if we are defining a function from B to A, so first of all, we cannot have two images over here, right? We cannot have two images in the codomain for a single element in the domain, right? So for one, we cannot have two images. So that is why it's not a function. Also, one element is not being defined, is not being mapped. Now, initially it was fine over here because B was the codomain, but here B is the domain part. So for in case of functions, B is the domain and every element has to be mapped. So 3 is not being mapped, and also these are divergent rays. These are the divergent arrows actually. So one is having two images in set A. That is also not possible as per the definition of function. So that's why inverse of many one function doesn't exist. Now let's try to define a function, define an inverse of a function in case of an into function. So this is a set A, this is set B, this is set A, this is set B. So let's add one more element 4 over here. Now let's try to draw an into function. So we can clearly say that this is an into function because every element of A is being mapped to B. So that defines the basic rule of function, but 4 is left over here. So codomain is not equals to range. So 1, 2, 3 is the range, but 1, 2, 3, 4 is codomain. Now let's try to define the inverse. So for that, we'll reverse the arrows, right? Now 4 is not being mapped to any element of A. That is against the rule of functions, right? So that is why we can clearly say that an into function, for an into function, inverse is not being defined because one element or one or more element of set B is not going to be defined or not going to be mapped. Sorry. Yeah. So that is why it's not, an into function does not have an inverse function. So that is why a function has to be bijective, basically 1 1 and onto for its inverse to exist. Now let's talk about functional equations. So what are basically functional equations? So let's first try to understand what are equations. Let's say we have one equation fx equals to x square plus 2x plus 3. Let's say we have this equation. So what is this equation? We have defined the function in terms of the variable x and some constants, right? Now what if I define fx equals to f of x plus 1 plus f of x plus 2 and maybe some other functions as well. So what we are doing over here, we are defining a function in terms of functions itself. So that's why it's called as functional equations, because we are defining the function in terms of functions itself, not in terms of variables called x or y, right? Now to solve these equations, we have two methods. The first one is iteration method and second one is replacement method. Let's try to understand these methods. So let's take an example first. We have been given over here that f0 equals to 1, f1 equals to 2, and fx equals to 1 by 2 times f of x plus 1 plus f of x plus 2. Find the value of f of 5. Now the main idea is over here to just plug in values and try to find the other values. So very crude way of solving any equation, right? So that is the iteration method. So you can clearly understand with the name that you have to iterate again and again to find the values. Or sometimes what you can do, you can make in different series. So let's say we have been given over here, we have to find some f of nth value, and maybe f of x plus n, where we keep on iterating till n value. In that case, it might be possible that we get a different series over here and the terms get cancelled out and we don't have to do the regular manual iteration, right? But in this case over here, we cannot see that we don't really think that we can make a different series over here. And that's why we have to do the manual iteration. So that is a very crude method to solve these type of equations. So let's try to solve it. So we have been given over here fx, 2fx basically equals to f of x plus 1 plus f of x plus 2. So what I'll do, I'll just rewrite it as f of x plus 2 equals to 2fx minus f of x plus 1, right? Now we'll try to put in the values. So we have been given f of 0 equals to 1, f of 1 equals to 2. So what I can do, I can find out the value of f of 2 from here by putting x equals to 0. So let's say x equals to 0 over here. Then what we'll get, f of 2 equals to 2 times f of 0 minus f of 0 plus 1, that is 1, right? So 2 times f0, that is 2, and f1 equals to again 2. 2 minus 2, that would be 0. Now we have got f of 2 as 0. I'll again put 1 over here. So what we'll get, f of 3 equals to 2 times f of 1, 2 times f of 1 minus f of 2. That would give me 2 times f of 1 is 4. 4 minus f of 2, 0, that is again that is 4. Now f of 4 would be 2 times f of 2 minus f of 3, right? So because what I have done, I have kept 2 over here, x equals to 2. Now what we'll get over here, 2 times f of 2 would be 0 because f of 2 is 0, right? Minus f of 3 minus 4, that would give me minus 4. And similarly you can calculate f of 5. So you can clearly see that we are iterating over again and again. What if we would have got equation like f of 0 minus f of 1. So if it was like this, f of x plus 2 minus f of x minus f of x plus 1, then it would have made much more sense to create a different series. Then we would have written as f of x plus 3 equals to f of x plus 1 minus f of x plus 2. Now you can clearly see that these gets cancelled out. So if you have to find the summation of all these terms, or maybe you have to find one singular term uh, by forming a series over here, then this would have made more sense. So that is another approach for different types of questions. But over here we just have to like rewrite things and again and again and find out the value. Now let's look at the second example in the second method as well, that is replacement example. So over here sorry fx plus 2 times f of 1 minus x equals to x square plus 2 for all x belongs to R. So when I'm saying for all x belongs to R, I can replace x with something else, right? So that's why I can clearly see that if I try to write f of 1 minus x over here plus 2 times 1 minus 1 minus x, then what I'll get over here, that is nothing but x only. That would give me 1 minus x square plus 2. Why I am able to do that? Because x belongs to R. X can take any value. So that's why I can do these kind of adjustments. Now, how I got the idea to do this? Because I saw that if I plug in 1 minus x over here, the terms get replaced and I get two equations. And when I have two equations and two variables, I can solve them for the value of fx. Now, this is simply two equations and two variables in fx and f of 1 minus x. You can clearly solve this for the fx value and you can get the fx value, right? Now let's try to solve some PNC problems in calling out the number of functions. So basically this is a very important topic in terms of PGDBA, and a few questions have been asked for this one. So let's try to understand this case by case. So there are three cases basically. Number of elements in set A equals to number of B, number of elements in set A is greater than number of elements in set of B, and number of elements in A is less than number of elements in B. So let's take the case one. So what we'll be doing, we'll be finding out five things for every case. So basically total number of functions, total number of onto into functions, and total number of one and many one functions. So let's try to find it out. So the first case over here is n equals to nb. So we have five elements over here. This is set A and this is set B, and na equals to and b equals to 5. Now let's try to understand total number of functions. Now just to give a recap, what are functions actually in terms of arrow diagrams? So basically what is the definition of functions? Now it says that every element of A should be mapped, and also there should be exactly one image, not two images. So basically it shouldn't be like this because it's diverging and it has two images in set B. That shouldn't be the case. This can happen. Multiple elements from set A can map to single element of B. That can happen. That is the case of many one functions. But the opposite cannot happen. That is the base case. And similarly, all the elements of set A should be mapped. Now, when I'm trying to write total number of functions, when I'm trying to calculate total number of functions for this kind of case, n equals to nb, I can clearly see that this element has 5 choices, and similarly, this also has 5 choices. So basically, this element can map to 1, 2, 3, 4, or 5, whichever it wants, right? So it has no restrictions. Similarly, B can also do the same. So every element has 5 choices for mapping. So basically, 5 into 5 into 5 into 5 into 5. So that would give me 5 raised to 5. So these are the total number of elements over here. Total number of functions over here, sorry. Now let's try to calculate the number of 1 functions. These are the total number of functions. Now we are calculating total number of 1 functions. Now let's say this is mapped to 2. Now 2 is being occupied. It cannot map to any other element because that would make it many one function. So basically, A element has this 5 possibilities. It can map to 1, 2, 3, or 4 or 5, right? So it has 5 possibilities. But now once this element is being occupied, any one element is being occupied. Now B has only 4 choices. It can either map to 1, 3, 4, or 5, right? So it has 4 choices. Similarly, when let's say B is mapped to 1 over here, now these two are occupied. We have got only 3 elements left. So I can easily say that C will have 3 options, E will have 2 options, and F will have 1 option. So that would give me 5 factorial. So we have got 5 factorial 1 functions. Now for many one, that is very simple. That would be total minus 1, right? That would be very simple. That would be nothing but 5 is for 5 minus 5 factorial. So this is our many one functions. Now let's talk about onto functions, total number of onto functions. Now the basic definition of onto function says every element of set B should be mapped. So basically range equals to codomain in addition to the basic definition of functions, right? So in this case, when we have number of elements in A equals to number of elements in B, so the only possibility left is singular mapping, right? 1 mapping. So basically every element of A is being mapped to just one element of B. That is the only possible case. I cannot do this. When I'm doing this, 2 is left behind, which is not possible for onto case because range is not equals to codomain. Over here, codomain is 1, 2, 3, 4, 5, but in this case, range would be 1, 1, 3, 4, and 5. That is not possible. So that is why this is the only case, or maybe this is the only case. Singular kind of mapping, 1 mapping. So basically, number of onto functions in this case is nothing but 1 functions. So that would again come out to be 5 factorial. And same with into functions. What would into functions be? 5 raised to 5 minus 5 factorial, total minus number of onto functions. So our case 1 is over. Now let's talk about case 2, and that is the trickiest case, A and B. Now let's talk about total number of functions. In case of total functions, we'll use the same concept that A has 4 choices over here, B has again 4 choices, C has 4 choices, D has 4 choices, and E has 4 choices. So 4.4.4.4.4.4, that would be 4 raised to 5. So we have total number of functions as 4 raised to 5, right? Now let's talk about total number of 1 functions. Now tell me one thing. I have done this kind of mapping. Now I can clearly see that E is going to be left behind. In any case, whatever the kind of mapping I do, one element in set A is going to be left behind, right? because we have just 4 elements in set B. So that is why we can clearly say that number of 1 1 functions is 0. And that's why many 1 functions would be 4 raised power 5 minus 0 total minus number of 1 1 functions. Now let's talk about onto functions. Now that is a tricky part. I'll take that in a new page. Total number of onto functions. Now one might get confused or one might get tricked that okay, what we can do, we can select 4 elements from here and we'll map it one to one from here. And what we'll do, we'll just take one element left behind and map it to another. So that would give me an idea that I would do 5C4. Basically, I'm selecting any 4 elements from set A. Let's say this, and this. So I've selected 5C4 in this manner, and I'll do 4 factorial to arrange to map them in this manner, right? In 4 factorial manner, and this one left behind. Maybe I'll mark it with some other pen, and this one left behind can be clubbed with anyone. So again, it has 4 choices, so into 4. That might give me the answer, but that is an incorrect way to solve it. Why? Let me show you how. Now let's say this is one case. In this one particular case, what is happening, we have selected 4 elements A, C, D and E. Now I'm left with B. Let's say I map it with one element of set B. So this is the case. Now let's take one more case. This is A, B, C, D, and E. This is 1, 2, 3, and 4. Now what I've done, I have selected B, C, D, and 4. When I'm doing 5C4, I'm selecting B, C, D, and E. And now I'm marking it like this: C2, 2, D2, 3, and E2, 4. Now I'm selecting A for this one. Now you can clearly see that these two are exactly same. The process was different initially. When I did the 5C4 value, 5C4 term, when I did consider the 5C4 term, I chose A, C, D, and E and mapped it differently. Over here, when I did the 5C4 term, I did B, C, D, and E and mapped it differently, but we got the same output, right? So basically, when we are doing this, we are actually repeating the cases, and the total number of cases are getting repeated, and hence the value is getting increased. So that is not the correct approach, and you might get confused in the examination for solving this one. So this is a little tricky one if you don't know the solution for this one. So let's try to solve this from the basics. So what can be the idea? So basically, we have to fill out all these numbers over here, all the elements of set B. We have to do that. So we should have 4 elements over here, because 4 groups maybe. Yeah, you should have 4 groups over here. So what we can do, we can combine 2 and we can keep these as individuals, right? We cannot combine these 2 as well, because that would give me only 3 elements. So we'll keep 3 as separate and combine 2. So we can again, now we can do the mapping easily. So for combining, what I'll do, I'll have to take 5C2. I'll take any 2 combination that would give me 5C2. Now once I have selected 2, so basically the rest of the 3 are automatically selected. I have selected 5C2 for the clubbing part, and now I have to arrange these 4 with these 4, right? So that would be 4 factorial. Very simple, right? So this is our answer. This is how we have to do it. Now talking about into functions, that would be total minus 5C2 into 4 factorial. Very simple. So our case 2 is also over now. Now let's talk about case 3. Let's talk about total. Now again, for total, we have a very crude way to solve it. So A has 5 choices, B has also 5 choices. So 5 dot 5 dot 5 dot 5, that would give me 5 raised to 4, right? That is 625. Now let's talk about 1 1 function over here. Now what can be done over here? We have 4 elements over here, we have 5 elements over here. So A has 5 choices. So it can map to 1, 2, 3, or 4 or 5. Let's say it's mapped to 1. Now 1 is being occupied. We have 4 elements left. And B is now left with 4 choices. That would give me 4. And similarly for C it would be 3, and for D it would be 2. So that would again give me 5 factorial. In this case, it's coming out to 5 factorial, right? Maybe for some other case, maybe let's say we have 6 elements over here. In that case, it would turn out to be 6 into 5 into 4 into 3. That won't be 6 factorial. But in this case, it comes out to be 5 factorial once again, because we multiplied 1 or not, that doesn't matter. But you got the idea how to calculate these. Now, similarly, manual one would be total minus 1 1. That would give me the answer. Now let's talk about onto. In case of onto, we know that no matter what we do, we cannot fill out these elements. We cannot map these elements completely. Let's say this is the maximum case. We are mapping one element with one element of A with one element of B. But still, this 4 is going to be left behind. I might use the different pen. So still this 4 is going to be left behind, because we have just 4 elements over here. We have lesser number of elements in A. We cannot do this, because that would refute the definition of functions, basic functions, right? Because we cannot have divergent things. We cannot have two images from set A in set B. So basically total number of onto functions is nothing but 0. So that's why total number of into functions is total minus 0. That would nothing but be 625.